Since there are 6 ways of arranging dx, dy, and dz, there are actually 6 different ways to set up the bounds for the integral over this solid. Let's look at 2 or 3 more. This time let's put the dx on the inside and then dy, dz outside. So if I want to integrate with respect to x on the inside, we can imagine sending a line through this solid parallel to the x-axis. So I'm going to come in from behind. I'm going to intersect that back plane, which is the YZ plane. I'm going to continue on the inside of the solid until I get to the surface, and then continue out in the direction of the positive x-axis. So one way to think about this is if this solid were made of Play-Doh, it'd be like taking some uncooked spaghetti and sticking it through the Play-Doh. We want to know the name of the surface where it enters and the name of the surface where it exits. Now where it enters is easy. It enters on the YZ plane, and the YZ plane has equation x equals 0. So x equals 0 is the lower bound for dx. The upper bound is going to be over here on the surface of the solid, which is the cone. So let's solve for x in the equation for the cone. 9x squared is equal to y squared minus z squared. So x squared is y squared minus z squared over 9. So if I take square roots, I'll get x equals plus or minus the square root of y squared minus z squared over 3. Now, the part that's in the first octant has a positive x coordinate, so I actually need the plus. So that's going to be my upper bound of integration for x. The square root of y squared minus z squared over 3. Now, to figure out the bounds for y and z, I want us to imagine taking this solid and taking its shadow in the YZ plane. So I'm going to collapse this to the right into the YZ plane. Let's capture just that part. If this is y and this is z, then in the YZ plane, I'm going to have a triangular shadow where this line segment is this one. This vertical line segment is this vertical line segment, and this horizontal piece is this edge along the y-axis. So let's see if we can find out an equation for this edge. Since this is in the YZ plane, we know that x is equal to 0, and if I set x equal to 0 in this equation, I get that z squared equals y squared. So z is plus or minus y. And since this is since z and y are both positive here, it'll be z equals y. We also know that the shape extends as far over as 9 on the y-axis. So since y and z are the same, this is the point, 9 along y and also 9 along x. So let's see if we can use that to figure out the bounds for y and z. Since I'm doing y next, I can draw a line segment parallel to the y-axis. Notice that it enters over here on the line, the slanted line, z equals y, and exits on this vertical line, which has equation y equals 9. So I enter on y equals z. So y equals z is my lower bound, and I exit on y equals 9, which would be my upper bound. And last of all, I give the smallest and largest values of z in the region. The smallest value of z is 0 along the y-axis, and my largest value of z is 9. Now notice now that I've done all this hard work having dx on the inside, it's easy to figure out what the bounds will be if I leave dx on the inside, but swap the dz and the dy. So the bounds for x stay the same. X is still going from 0 to the square root of y squared minus z squared over 3. But I'm going to have to change the bounds on z and y. Since I'm hitting z next, I'm going to draw a line segment through here, parallel to the z-axis. Notice that it enters on the y-axis, continues on the inside, and exits on the line z equals y. So that means that I'm entering on z equals 0 and exiting on z equals y. So my bounds for z are from z equals 0 to z equals y. And finally, putting in the smallest and largest values of y, I'm going from y equals 0 to y equals 9. So we've done 4 of the 6 different orders. Let's do maybe one more. After I write the problem down, you might want to pause the video and see if you can do it yourself, and then I'll work it out. This one might be a little bit tougher. Let's see. Notice that this integrand z has nothing to do with the bounds. It doesn't matter what function we sit in here. The bounds are all based on the solid, not on the integrand. If you want to think ahead of me while I draw the picture, let's do dy, dx, dz. Okay, so there's my solid. If I want to put the dy on the inside, then I want us to imagine drawing a line that comes in parallel to the y-axis. Notice that this time it's going to enter on the cone, continue on the inside, and exit on this plane, which is parallel to the xz plane. Now recalling that our original solid ends over at y equals 9. Y equals 9 is indeed the equation for this planar face. And that's going to be my upper bound for y. Now for my lower bound, I need to rewrite the equation for the cone in the form y equals. So the cone, looking for the equation, I erased it. The cone was z squared equals y squared minus 9x squared. So let's see if we can rewrite that in the form y equals. I'll add 9x squared to both sides. So y squared equals 9x squared plus z squared. And then taking square roots, y is plus or minus the square root of 9x squared plus z squared. Since y is positive, it's the positive square root that I need. So my lower bound over here has equation y equals the square root of 9x squared plus z squared. Now let's imagine taking the shadow of this in the xz plane. Now notice the shadow is not simply this dot where it touches it, but if I were to take a light and shine it back along the y-axis, I would see a shape like this kind of triangular shape in shadow on the wall represented by the XZ plane. So let me draw it kind of the way it would look if we just turn this shape this way. The z-axis would be pointing up and the x-axis would be pointing to the left. This corner would be mapped to the origin. This corner would be mapped out along the x-axis. And this corner would be mapped onto the z-axis. And this piece right here, which is part of an ellipse, would look like part of an ellipse right here. So the shadow in the XZ plane would look something like that. Now this edge is not actually in the XZ plane. It's over here where y equals 9. So let's imagine, to figure out what the equation for this edge is, let's take y equals 9 and substitute it into this equation. If y is 9, then I would have 81 equals 9x squared plus z squared. So the equation for this piece of the ellipse is 9x squared plus z squared equals 81. So again, remember this is not in the XZ plane, it's hovering above it in the solid in space. So now let's set up the bounds for x and z using this picture. Since I have x next, let's send a line segment through here, parallel to the x-axis. So from the way I've oriented it, I'm going from right to left. Over here, I have the z-axis, which has equation x equals 0. And this point, where I exit, is going to be on this ellipse. So let's solve for x in that equation. We'll have 9x squared equals 81 minus z squared. So x squared is 81 minus z squared over 9. And taking square roots, x is plus or minus the square root of 81 minus z squared over 3. X is positive, so it's the positive square root that I need. So for my x's, I'm going from x equals 0 to x equals positive the square root of 81 minus z squared over 3. And then last of all, I need to figure out what my bounds on z are. So the smallest value of z in this region is going to be at z equals 0. And the biggest value of z is going to be up here where this ellipse crosses the z-axis. So it's going to cross the z-axis when x equals 0. And notice that x equals 0 when z equals plus or minus 9. So this is a positive point, and that's going to be z equals 9. So setting things up with the order dy, dx, dz, these are the bounds that we get. And just to test yourself, there's only one way left to do it, and that would be dy, dz, dx. And you should check to see if you can set up the bounds that way.